So just to give that summary, a chemical reaction is where we have something new, where we look at the chemical formulas of our reactants and they're now different with our products. So one of the most important things is whatever we start with, that's what we're going to finish with. So we're not going to actually add any new elements in that process. The atoms that we start with, the types of atoms, are going to be the same types of atoms that we finish with. So these are the signs. These are the signs that we could make, these observations that we can make that a chemical reaction has taken place. Now, some of these could be the case just for a physical change. Okay, so we'd need a few observations to then decide that this is what's taken place. The other thing that we could look at is the rate at which this occurs. How fast does our reactants become products? And then what would be the factors that influence how fast those things happen? Okay? We can quickly, if you've got some off the top of your head, you can throw them at me. Otherwise, later on, we'll have a little bit of a look at what those might be. Has anyone got anything that they might think could affect how fast these reactants become products? Yep.
How reactive they are.
How reactive they are? In what way?
Like the elements on the far left table react.
Yep, so that might be the case when we're setting up our reactants. So with our reactants, are they even likely to react at all? And then how reactive are they? So the alkali metals, as we move down, they become more reactive. Therefore, the reaction might occur quicker. Yep. Yep.
How much reactants we're using?
Excellent. So the concentration? Beautiful. So I'll just put a couple of these down. So maybe the reactivity, but we'll go through them more later. The concentration. Anything else? Yep. Temperature. That's a key one that always is important. Okay. If we didn't have proteins that denature in our body, like our enzymes, we would benefit from being really hot because our reactions would go much faster. Okay. But at certain temperatures, some of our parts start to break down, so it's bad. We could also look at the ratio of reactants and maybe things like surface area. So is it one big chunk or is it finely chopped up? So all these things are going to affect how fast that reaction occurs, and then these are the signs that something's going to actually happen. Okay? So if I had this cube, that has a volume, I can have a same cube of that same volume, but I could separate it into 4 pieces. So I've got the same volume, but now I've got additional surfaces. Okay? And I'd probably need 8 cubes there. Yes?
Volume factor as well as surface area?
It's more the ratio between the two. So volume, we can then sort of look at, is that volume representing a concentration? And then compared to that volume, how much of the surface area is exposed? So the bigger that surface area with the same volume is going to create a much faster reaction. That's why when you go to Coles, they don't just have one checkout. They have 10 checkouts. Or they have a checkout that snakes so that there's more people can access the checkouts at once. Increasing the surface area, but keeping the volume of the store the same. Okay, so let's have a look at, I've got a substrate here called hydrochloric acid. Okay? And I want to do something with that acid. Okay? In fact, does anyone know the chemical formula for hydrochloric acid? H. That's it? H what?
CL.
HCl. HCl. That is the formula for hydrochloric acid. So what atoms make up that compound? Hydrogen and chloride, or chlorine. So you've got hydrogen and chlorine. Now you might, from what we've learned so far, go, oh, I'm going to call that hydrogen chloride. Okay? Because when these are added to solution, that hydrogen leaves, it makes an acid, and therefore anything with these hydrogens that can become free, we call acids rather than, say, hydrogen chloride or something like that. Okay? Now, my challenge to you is I want to get the hydrogen by itself. I want the hydrogen. I'm going to give you a few minutes to have a think about that, because we're going to make a chemical reaction occur. I want the hydrogen. I don't want it in the acid. I want it separate. I want to be able to collect it. Okay? How can we do that? So we've had one suggestion that we could add a substance with the hydrochloric acid, hope that reacts and then releases our hydrogen from that. Now, Andrew just said maybe that substance is sodium.
So you said children are dying, so you can't really take that chance of it might do it.
Yeah, we've got to practice first. Otherwise, they're going to die because if we do nothing.
Wait, how does hydrogen help dying children?
How are they going to die?
Maybe you light the hydrogen on fire, use it for energy, and then they all survive.
You don't get a lot of hydrogen.
How do you know?
Because I remember doing it before.
Okay, so we'll just have a look at quantities. Okay, so Andrew says it might be sodium. Okay, so going to what we can do and what we can't do. Okay, we can't just leave the hydrochloric acid by itself and just magically think that it's just going to now release all its hydrogen. Okay, we need something to help it to react. Okay, what else can't happen? Well, we can't have the things that we add together just suddenly disappear, can we? So if we add sodium on this side, we're going to get sodium on this side. So in some way, we're going to get sodium here, and we're going to have chlorine here as well in some form. Okay? Now, the types of things that would actually happen is that sodium would react with the hydrochloric acid, and it would displace or push out the hydrogen from that compound. It would replace it. It would then form into bubbles. Okay?
Catch the bubbles.
And then we could catch those bubbles. So we could put a balloon on top or anything and we could catch those bubbles. Okay? But what's going to happen with the sodium and the chlorine? Remember our party analogy.
Makes salt.
It's going to make salt. So they're going to join together and leave our hydrogen. Okay? So that's how we can use reactions to our favour. If we react things together, then we can predict and produce products that we're interested in. So in this case, we're going to produce hydrogen gas and sodium and sodium chloride. Now, to get a better understanding of that, instead of just having it as words, we'd actually like to write out the chemical formulas. So, challenge number 2. I'd like you to write out this word equation, and then I'd like you to convert each word compound into a chemical formula. I'm going to see if you can do it. Who can give me the chemical formula for any of those things? Andrew.
HCl, Na.
Na plus HCl, arrow, hydrogen gas. H. What have I taught you about gases? They're lonely. H2. So they're going to exist in pairs. And sodium chloride?
Knuckle.
NaCl. Okay? So let's just have a look at sodium. Now, we've just represented sodium as Na, its symbol for its atom. Does that mean we just have one atom?
Not
Two?
maybe.
We would have billions. Remember, you get a chunk of sodium, which I think we saw, or we might not have used sodium. That's going to have billions and billions of atoms in it to make up that size of sodium. But we don't represent it as Na 1 billion because it doesn't really matter how many they are because it will react regardless. Okay? So we're more interested in the ratio of these things, not the amount of them. Okay? So we're saying we've got one Na for every blah HCl. And in this case, the HCl also, it doesn't matter how much we have, they're going to react together. Yep.
Do you have to make all of the other, everything else in this equation double because to balance it out?
Okay, let's have a look at that in a sec. Okay. So, we've got now our equation written as chemicals. But what is the thing that we can't do? We can't have substances disappear. We have substances being created out of thin air. We started with one hydrogen, and now we're getting two. So, I'll give you an opportunity to now balance that equation. So when I was first learning, this was the method that I used. Okay, the first thing I did was I looked for polyatomics. The second is I list the elements on each side. So if we go to step one, were there any polyatomics? No. And if you're like, what's a polyatomic again? We'll get to that later. But if we can look at polyatomics on either side and keep them together, it makes our balancing much easier. I'll show you later. But this one doesn't have any, so we're going to go on to step two. List the elements on each side. Okay, so we've got Na, we've got H, and we've got Cl. I'm going to do the exact same thing on the other side. Na, H, Cl. And all I'm going to do is count them. Because if they're already balanced, they're already the same on the left as the right, I don't have to do anything. My life's easy, I love it. Okay, so how many sodiums do I have? One. How many hydrogens?
One.
How many chlorines?
One.
Okay, 1, 1, 1. So I'm looking for 1, 1, 1 on the other side. Okay, then I know it's balanced. How many sodium?
One.
How many chlorine?
Two. Wait.
Oh, see? See what I did there?
Yeah.
How many chlorine?
One.
And how many hydrogen?
2.
So it's not balanced. I'm like, no, now I'm going to have to use my brain.
You were doing that
Okay.
dramatic.
I was. Okay, this is video. This is YouTube.
Yeah.
It won't be on YouTube. But anyway. It'll at least be private anyway. We now need to make them even on both sides. Because the law of conservation of mass means that matter can't be created or destroyed. It can just be converted into different forms. Okay, so who would like to tackle this? There's a couple of ways. Most people just look at the one that's bigger and then make the one on the other side that needs to be bigger as well. Okay, so for example, we've got 2 hydrogen here. I want 2 hydrogen. Where can I put the numbers?
On the left side.
Only in front of the compounds or the elements. I can't put them behind. I can't change that chemical formula in any way. So I'm going to put a 2 here. What's going to happen to the hydrogen?
It's going to go to 2.
That's all?
No, because now chlorine has 2.
Excellent. So if you don't get that at the start, you'll never be able to balance anything because you'll stuff it right up and you'll be like, oh, this is so hard. So you need to get those foundations right. Okay, so now I look, is it balanced? 1, 2, 2, 1, 2, 1, not balanced. So now I can go back to the chlorine and get that one the same. Put a 2 here. You can make these dramatic effects in your brain. So now that's a 2. And now that's a 2. So now I'm 2, 2, 2, 1, 2, 2. What do I do?
2 sodium.
2 sodium. Now, is it balanced?
Yeah.
222, 222. We are now successfully balanced our chemical equation. So we know that we need 2 sodium for every 2 hydrochloric acids. Okay? And that will make a hydrogen gas molecule as well as 2 sodium chloride compound molecules. Okay? Sound good?
Yeah.
So let's add that third step. Okay, after we listed the elements, we counted them, and then the fourth step is we moved back and forth between the reactants. So moved back and forth between reactants and products adding, now I'm going to use the technical term here. So if this was algebra and that Na was an X, what would the number in front of an X be called?
Coefficient.
Oh, geez, you guys are good. So we're adding coefficients, okay? We're not changing the terms, which is in this case, our formulas. We're adding coefficients. Okay? Remember, maths and science, same. All right? That's the only thing we can do. And we keep going back and forth until they're balanced.